So David asked me to talk about some heterogeneous trees in fact, but some non-regression methods. So I'm a statistician, and so I picked the word machine learning. Which, to me, the difference between machine learning and statistics is really vague. So anyway, I'm going to talk a few of those methods. Okay. So HTE and machine learning are the two buzzwords in comparative effectiveness research. So a very hot trend in the field of causal inference in both statistics and economics in recent years is to use machine learning to infer HTE. So particularly in this, again, another buzzword, big data era. Again, even though nobody knows what does that exactly mean. So actually the central goal from a statistical standpoint is actually the same as the traditional regression methods. So what the goal there is try to accurately learn from the data, accurately learn the outcome function, the outcome surface, given the covariates and the treatment variable. The goal is the same, it's just some new analytical methods. So before I introduce those methods, usually the impression is machine learning methods are usually more flexible and adaptive. So that's good. But it also has a lot of limitations, and certainly is not panacea. It's not the cure to everything. So I'm going to very quickly browse through four types of popular methods, machine learning methods for HTE. So again, many of you know those. I just quickly run through them, not really getting into the technical details. The first one is the so-called penalized regression that has been used in the study, I think in Basu's study earlier in the panel 1. Again, it's not, for people who don't know this, it's not, you don't penalize regression. You penalize the complexity of regression. Right? So you basically, method lasso, elastic net, this nice methods. Essentially what you do is, remember, in a regression setting, what is HTE? Essentially, it's the interactions between the treatment variable and those covariates. And so you have a regression, you can throw in a lot of these interactions. Many of them actually don't mean anything, but this type of regression essentially have a way to select the most important and meaningful interactions. So that's called penalized regression, and that's used a lot. So the second is the regression tree-based methods. Many type of them, the card, random forests, and that is also I'll talk a little bit later with more detail. Then third is called the Bayesian nonparametric models. This is getting a little bit more advanced in terms of mathematics, like Gaussian process, Bayesian trees. They also have their own pros and cons. I'll get there. And the third is the last one is so-called ensemble learners. So many of those previous methods, like the tree-based method, if you just do one model, actually it might be a weak learner. The performance might not be good. So the idea is, okay, I'm gonna do a bunch of them and combine them. So that's the name ensemble learning come from. Like boosting. Essentially, forest is a type of, you assemble a bunch of trees. So those are all broadly called supervised learning methods. Those methods are all in their original form. They're all built for prediction. Again, in statistics, there is a subtle difference between prediction and estimation, right? So but when we talk about HTE, it's slightly different, because HTE essentially, the fundamental problem is you want to study the fundamental problem called the inference. You want to see, so this one patient under one treatment condition versus counterfactual, hypothetically, had this person being treated the other way, right? So that is actually, you never see that at individual level. So that is the HTE, actually the fundamental problem of HTE. And all those prediction methods, they were originally built for this purpose. So they all need to be repurposed, so modified for this purpose. So that's what happened in the last 5 years, or actually 10 to 5 years in the causal inference literature, try to adapt those. So tree methods, I need to keep on time. Oh, this is time, right? Oh, okay. So I have plenty of time. So just go a little bit about the regression tree. So now I go to the details. Remember, I will skip the penalized regression because that is think, easier to understand. So the tree is the first method I get there. So tree, essentially, in the original form, you just participate, instead of build a x equals time, y equals x times beta, that kind of regression form, you partition the covariate space into leaves, essentially into subgroups. So then you predict the response in each leaf, each subgroup, use a sample mean in that region, that subgroup. And then, of course, the key is how do we grow a tree? Where do you decide, split to split the leaves? And so there's, I think this. This is a very simple two-variable tree case. So it's like if you have two variable, one x1 and x2, so you decide first split at the x2 at the point. If it's someone has x2 below a threshold, then you go to this leaf, and then the other way, go to the other leaf, and then you decide to further split, things like that. So you do that kind of thing. So you select tree complexity, use cross-validation, some method to decide what tree, how deep the tree you're gonna get, and then you also do some pruning and all that kind of thing. So again, that was originally made for prediction, and it modified recently for HTE estimation by this pretty landmark paper, Anzi and Imbens 2016, PNIS paper talk about how to adapt that into the HDE setting, and also more recently extend to causal forest by Anzi and Vega 2017 JATA paper. Again, this is just the first, one of the most important one. There are just a huge amount of papers, probably hundreds of papers now written in the last 2 years actually to do this type of thing. And so I'm not going to technical details. The key is to, as I mentioned earlier, a single tree is usually a weak learner. You can grow one tree, so average over a bunch of trees, then you get the forest. So improve the estimate usually. So this is all their tree-based methods. So they all have pros and cons. So the pros really about the one big pro of tree-based methods is they're very easy to implement. So there are a lot of softwares, built software, and they need to be adapted again for HTE, but there's still plenty of software, and they're also pretty fast because the computation is fast. So those are the pros, and the cons is actually very often we find that the tree methods tend to underestimate uncertainty. So you get a tree, and then you get a forest, and you think that's it, but if you do the uncertainty quantification is often go a little bit conservative there. And second thing is that's more mathematical is the tree methods usually have this restrictive structure in the sense that it essentially assumes that this tree structure stand everywhere in the whole parameter, the whole covariate space, the multi-high dimensional space. And that again is not always the case. So I should put a graph here to show you some simple examples that is a bit restrictive, but it's still very popular. So then that leads to the second type of method, Bayesian nonparametric methods. Again, I'm pretty sure this is pretty far. This is a type of method. There's a huge gap between the methodologist and the practitioner. So broadly, Bayesian statistics, you use the Bayes theorem to combine the evidence from the previous knowledge, prior distribution, and the data, right? So then if you have a regression, you put this mysterious prior distribution that summarize your previous belief, and then you run it, then you update it, use the data to get the posterior distribution. So that is Bayesian, the Bayesian paradigm. So of course, then you can build the same thing. It's just any methods, you throw a type of prior, and then you can get the Bayesian counterpart to it. So the tree method I just described, of course, you can throw a similar type of some priors, and then similar to regression tree, but it's just implemented in the Bayesian paradigm. So that is not something too exciting. It has some own benefits. But then this type of thing, the Gaussian process, is another very promising thing, but it also comes with a lot of disadvantages. So I put this reference. This is a book. It's a Gaussian process for machine learning. So it's a very good, well-written book. Talk about this whole general idea. So how do I describe this? Is a hard when I get the equation free. So Gaussian process is complicated, but how I summarize this, it's a very neat, it's a stochastic processes that extend the multivariable Gaussian distribution. You know, people talk about multivariate Gaussian distribution, normal distribution. It's extend that to infinite dimension. That's all you need to know. So it's this very mysterious thing that just fit this smooth curve everywhere and do wonderful things. Except it's very hard to fit. So Gaussian process give much flexibility in the model building and has a lot of theoretical advantages because, again, the core of that is still Gaussian. We know Gaussian is great, right? The Gaussian distribution is the regression, is the core of everything, and the Gaussian process is just push it to the even higher, infinite dimension. Okay, so the pros, the whole Bayesian nonparametric method, they're also Bayesian, the polyar tree, they're other things. But in general, Bayesian nonparametric methods, they incorporate prior knowledge. And because it's Bayesian, it has automatically uncertainty quantification. That's always cool. That's equals, you can immediately get standard errors. Well, not immediately. Once you've done this, you get the standard error. You don't need to do some bootstrap stuff to do that. And another thing is it works for small samples. I mean, it doesn't rely on some large sample theory. And the last one, I don't know, it works much to practitioner, but at least as a methodologist, it's elegant. It's philosophically and mathematically coherent and elegant. I don't know whether it works much, but I think it's cool. And then the cons are actually huge. The computational, that's why actually people don't use that often. So its computation is very demanding, especially when you have a high dimension, a large sample, the scalability is always troublesome. And another thing is the sheer mathematical sophistication for the lay audience is a big hurdle. And also the choice of prior distribution, how do you choose the prior distribution? And all of this, also the lack of software, like very usable software, make it very hard. It's very hard, it's not very accessible to a lay audience. But it has a lot of potential, there's a lot of work to do. Okay, so now a summarized page, or my view on this. So much recent, again, there's a lot of work underway, try to incorporate all the methods I described into the HTE estimation domain. And I'm doing something like also some such kind of research. So much recent advance in theory, both in statistics and economics. But one thing, there's a huge gap. The direct application to health studies is still pretty sparse. So there's a huge gap between theory and practice here. And more translational work is needed. And so there's this Powers et al. 2018 recent statistical medicine paper actually described, they compared a bunch of machine learning methods, tree and boosting, the causal boosting, they updated it to HTE and I think they did simulation study. Did I do real application? Anyway, they compared it. So they also, it's like in the last 22 years, there might be like 10 different new methods coming to market the statistical community. And you actually don't know, there's not much known about the empirical comparative performance of those methods, and that is needed. And also software development is key. Many of those methods, again, without software, is just sitting there on the shelf and nobody's gonna use it. And so this really requires effective collaboration between statistician and whether you call them machine learners or statisticians or data scientists, it doesn't matter to me, but it's essentially the methodologists and the clinical researchers. So people need to come together and then make this thing really, make this wonderful theoretical development useful in practice. And the last point, I think Michael will also make that point, is one must organically fuse traditional statistical tools and machine learning to reach better comparative effectiveness research. I say this is because the traditional statistical tools, what I meant in this specific context is the general framework of the potential outcomes, or the counterfactual framework for causal inference. And then you hear about all the propensity score methods and the instrumental variable methods, and those are all quote-unquote more traditional statistical methods. And then you have this new trend of machine learning, sounds very trendy and everything, but this too has to be, you cannot just put them to get stuck one on top of each other because they have subtlety. So one have to organically fuse this there's two directions to really reach better HTE estimation in general health studies. So I'm good on time. 5 seconds.
Thanks so much.